Joins are one of the most common operations in data engineering, but they can also become one of the most expensive parts of a Databricks job. When Spark joins data, it must decide how to bring matching records together. If one table is small, Spark can often use a broadcast join. The small table is copied to all executors, and each executor joins it locally with its part of the big table. If both tables are large, Spark may need a shuffle join. That means data is moved across the cluster, so matching keys meet in the same partition. The right join strategy can save both time and cost. In this video, we will compare broadcast joins, shuffle joins, sort merge joins, join keys, expensive join symptoms, and practical optimization tips. The first join decision is table size. A small table, like a dimension table, usually has fewer rows, smaller size, and lower memory impact. A big table, like a fact table, can have hundreds of millions of rows and much higher memory impact. When one side is small, a broadcast join often works well because Spark can copy the small table to every executor. This avoids shuffling the big table and usually reduces network and disk cost. But when both sides are large, Spark usually needs a shuffle-based strategy, such as a shuffle hash join or a sort merge join. Large tables are expensive to move, and table size directly affects join cost. Takeaway: table size is the first join decision. A shuffle join is used when Spark needs to move data from both sides of the join across the cluster. The goal is to place matching join keys together. First, Spark writes partitioned shuffle data from the current stage. Then data moves across the network. Next, the following stage reads the shuffled data and brings matching keys together. This creates a stage boundary because the next stage cannot fully continue until the shuffle output is available. Shuffle joins are common when both tables are large and cannot be broadcast. They are powerful but expensive. They create network traffic, disk input and output, and longer stage duration. The key idea is simple. Moving data is the cost of a shuffle join. A broadcast join is usually preferred when one side of the join is small enough to fit safely in memory. Instead of shuffling both tables, Spark sends the small table to every executor. Then each executor joins its local partition of the large table with the broadcasted small table. This can be much faster because it avoids a large shuffle across the network. Broadcast joins are excellent for one small, one large joins, such as joining a large transactions table with a small product or customer dimension table. However, broadcasting is not always safe. If the broadcast side is too large, it can create memory pressure, executor failures, or slow performance. Broadcast joins reduce data movement, but only when the small side is truly small enough. A sort merge join is a common strategy for joining two large datasets. It usually works in 3 steps. First, both datasets are repartitioned by the join key, so matching keys land in the same partitions. Second, each partition is sorted by the join key. Third, Spark merges the sorted partitions and outputs matching records. Sort merge join is reliable and can handle large datasets, but it pays for that scalability with extra work. It requires shuffle, sorting, and more disk and memory usage. This is why sort merge joins can be expensive when data is large, partitions are not balanced, or join keys are skewed. Takeaway: sort merge join is powerful, but it pays for sorting and shuffling. Join keys control the matching logic, and they strongly affect both correctness and performance. Good join keys have the same data type, same format, and same meaning on both sides of the join. They should also have a healthy distribution, so work can be spread evenly across tasks. Bad join keys can create serious problems. A hotkey can overload one task and cause skew. Null-heavy keys can create missing matches or wasted processing. Mismatched data types, such as integer on one side and string on the other, can prevent matches or force expensive conversions. Duplicate keys can multiply rows and create row explosion. Good join keys improve both correctness and performance. Before blaming Spark, always check the join key quality. Joins become expensive when data movement, imbalance, and input and output pressure grow. If both tables are large, Spark may need to move a lot of data across the cluster. If the join triggers excessive shuffle, network traffic increases and stages become longer. If join keys are skewed, a few tasks become much slower than the rest. If rows are wide or too many columns are selected, Spark moves more bytes than necessary. If filters are applied too late, unnecessary data enters the join. If memory is not enough, Data spills to disk and the job slows down even more. A wrong join strategy can also increase cost. The symptoms are clear: long join stages, high shuffle read and write, disk spill, slow tasks, and high cost. To optimize joins, focus on moving less data, balancing the work, and choosing the right strategy. First, filter early. Remove unnecessary rows before the join. Second, select only needed columns. Wide rows increase memory and shuffle cost. Third, broadcast the small table when it is safe and appropriate. Fourth, choose better join keys. Use consistent data types, clean formats, and keys with good distribution. Fifth, repartition only when useful. Repartitioning can help balance work, but it can also create extra shuffle. Sixth, reduce skew, using techniques like salting, bucketing, or skew hints when needed. Finally, keep optimizer statistics fresh so Spark can make better decisions. The best optimization is often reducing the data before the join happens. Spark UI can turn slow joins into visible evidence. Start by finding the slowest stage, sort stages by duration, and look for join-heavy stages. Then inspect shuffle read and shuffle write. Large values usually mean Spark is moving a lot of data. Next, check spill. Memory spill or disk spill during a join often indicates memory pressure. After that, review task duration. A long tail of slow tasks may indicate skew or uneven partition sizes. Also check executor data read. If a few executors read much more data than others, the join workload may be imbalanced. Warning signs include one stage taking much longer than others, very high shuffle, high spill, long tasks, retries, or failures. Spark UI helps you see it, understand it, fix it, and speed it up. Let us finish with a simple decision workflow. First, ask, is one table small? If yes, consider a broadcast join. The small table can be sent to all executors, avoiding a large shuffle. If no, ask, are both tables large? If yes, Spark will likely use a shuffle join or sort merge join, where data is redistributed by join keys. Next, ask whether the join keys are skewed. If they are, handle skew with salting, repartitioning, skew hints, or other techniques. Then check whether there are too many columns or rows. Filter early, select fewer columns, and reduce the data volume. Finally, validate in Spark UI. Check stages, shuffle read and write, spill, skew, task time, and overall input and output. Pick the strategy, validate the cost, and optimize the bottleneck.